Alright, so this video is going to be about common ions and an introduction to buffers. So the common ion effect in most textbooks is treated like it's something brand new, and it's really not. It's Le Chatelier's principle. And it's occurring when we add an ion that's in an equilibrium reaction. Okay, and then it causes the reaction to shift. So when we have a weak acid that dissociates, it produces a conjugate base, right? So if this is our acid, and it produces this conjugate base in small amounts, and it also produces hydronium ion. So we can add a salt of that conjugate base, like Na, and Na anion, or potassium anion, and this is completely soluble, right, because it's sodium, and sodium ions are always 100% soluble, so it ends up adding that ion to the solution, and it causes the reaction to shift away from the acid part, right? This is what makes the pH low. So if this goes down in response to this shift, if H3O has to go down, then that means that the pH is going up, because lots of acid, lots of H plus or H3O plus, same thing, means that it's going to have a low pH. So if this is going down, it's going to have a high pH. Well, acetic acid, when it's added to water, makes acetate, that conjugate base, and it makes hydronium. So we could add something like sodium acetate, right, or potassium acetate. Both of those are very soluble, and it will basically be adding sodium ions and acetate ions to the solution, which would then increase this. So if the acetate concentration goes up, the reaction would shift to the left, which would make the H3O go down, and the pH would then go up. And then down here, if we add CH3NH3Cl, okay, to a solution of methylamine, the CH3NH2, how does this affect the pH? Well, this here is a base, right? And this is its conjugate acid. So this is the salt of a conjugate acid. So chlorides are soluble unless it's with silver, lead, or mercury. Lead 2 or mercury. So if this is going to be soluble, then we're really adding conjugate acid. If we write the reaction for the base, it's going to be methylamine, the CH3NH2, plus water, dissociates to give CH3NH3 plus OH. All right, so that's the reaction. So if we add this salt and it dissociates completely because it's soluble, then we're increasing this concentration. So this is going up, and if we increase on one side, it has to shift to the other side. So it'll shift left, which means hydroxide then has to go down because it has to be consumed. So if hydroxide decreases, that means that the pH decreases with it, because high OH means high pH and low OH means low pH. So the pH will actually go down. In this example, we're given some information, and I think that's just to save us some time. So it says the concentration of hydrogen ion in a 1 molar solution of hydrofluoric acid was found to be 2.7 times 10 to the negative 2 molar, and the percent dissociation is 2.7%. So it says calculate the hydrogen ion concentration and the percent dissociation of HF in a solution containing 1 molar HF and 1 molar KF. And the Ka is 7.2 times 10 to the negative 4th. So if I write out my reaction for the acid, okay, acid is not going to ever react with its conjugate base. All right, so we have a solution containing these two. It doesn't say those two are going to react together. We just have a solution containing those two things. So I'm going to write my normal reaction for the acid, the main thing. And this right here will dissociate completely into potassium ions and fluoride ions. So we're really only care about the fluoride ions because the potassium ions are always spectator ions. They don't participate in the reaction. They just kind of float around and watch everything happen. All right. So if we write a Rice table for this, and we have 1 molar HF, and we have 1 molar KF, which means we'd have 1 molar F, right? Because if we have one of these, then we get one of each of these. All right, water doesn't matter because it's a liquid, and we don't have any of this initially. So this is going to decrease while this side has to increase because we don't have any H3O. We get X, 1 plus X, 1 minus X. And with all equilibrium problems, you should always write the equilibrium expression. So the Ka is going to be equal to hydronium times fluoride over HF. That will sometimes get you a point, even if it's not asked for. Now I'm going to plug in my equilibrium values into the K. So I get X times 1 plus X divided by 1 minus X is equal to 7.2 times 10 to the negative 4th. Now I can get rid of these X's, they'd be negligible. And if I multiply by 1 and then divide by 1, my X is equal to 7.2 times 10 to the negative 4th. So that is my hydrogen ion concentration. So you can see that it's much less here than it is here. So this is just HF. It's as if you had 1 here, 0, and 0. So by making this fluoride concentration 1, it increased over here and shifted this way. And what that did was decrease the amount of H3O that was produced, the amount of acid that was produced in this reaction. And so the percent dissociation here, 7.2 times 10 to the negative 4th, is the H. And that's going to be put over the HA, which is going to be 1 times 100. So that's going to be 7.2 times 10 to the negative 2nd percent, right? Because you multiply by 100. All right, so that's the percent dissociation. And the pH would also be much higher because you take the negative log of this to get the pH here. And you take the negative log of this to get the pH here, and those values would be 1.57 for this one and 3.14 for this one down here. So the pH went up quite a lot just by adding the conjugate base. And guys, you're adding base, the pH should go up. Even if it is a salt base, it's still base. What we're actually making there in that last problem is a buffer, and buffers are made when the solution has a weak acid and its conjugate base. Okay, so those two things. And the conjugate base has to be much higher in concentration than when it's just the weak acid dissociating. So if you just have HF dissociating into H plus and F minus, that is not a buffer because this is so little. Okay, you have to actually add the salt there or add something to HF to produce enough of this for it to be considered a buffer. They have to have very close concentrations. All right. We can also make a buffer by using a weak base and its conjugate acid. And the same can be said about the conjugate acid as we said about the conjugate base above. All right, so it's not enough that we produce the conjugate acid just from the base. We have to actually put extra conjugate acid in there for it to be considered a buffer. All right, so the best buffers are when the concentration of the acid and the base are equal and have high concentrations. So if you have a question that asks you which buffer would be best, you're looking for the ones where the conjugate acid and base, or the acid and the conjugate base, have close to equal concentrations, and those concentrations are high. All right, so if we have this acid and we add something to it, we add strong acid to it, so we're adding H3O. Okay, what is going to happen for this to neutralize that acid? Well, this H3O will react with this. And so it's going to shift the reaction this way, but only slightly, because then it has to get back to equilibrium. All right, so now if we add strong base, if we add OH to this, well, that's going to react with this and shift the reaction forward, so it makes more acid, and so the pH actually stays, it takes longer for the pH to change dramatically because we have both acid and base in solution. So with buffers, we have both the acid and the base in higher concentrations, and so they can neutralize the addition of strong acid and strong base easier. So we have NH3 in water. Okay, and we have plenty of this, and we have plenty of this. All right, so it's been put in the solution. And we add strong acid. Well, we're going to add H3O. And so the H3O gets neutralized by the OH. Okay? Or it can force the NH3 to react more easily. Right? In either case, the reaction is going to shift in a way to where it shifts this way, and then it gets back to equilibrium. All right? So the pH will change, but it will change very slightly. It will not change very dramatically. All right, and then how would the solution neutralize the addition of a strong base? So if we add strong base to this, then we would have NH4 reacting with hydroxide to produce NH3 and water. Okay, and in this one, if we add strong acid, we would have NH3 react with the acid to produce NH4 plus the water. All right, so if you add acid, it can react with the base, and if you add base, it can react with an acid. Acids will not react with acids, bases will not react with bases in an acid-base reaction. All right, so this is the Henderson-Hasselbalch equation, and this equation is used to calculate the pH of a buffer. You can use a rice table like usual, or you can use this equation. So in these equations, the acid and the base have to be conjugate acids and bases. It can't just be acid and base. All right, it can't be OH and your weak acid. They have to be conjugate acid-base pairs. So when we calculate the pH we're going to calculate the pH of these solutions, and I'm going to do these calculations using a rice table and the Henderson-Hasselbalch equation. And the Ka for this acid, which is the same acid here, is 1.8 times 10 to the negative fifth. That's my reaction. Okay, and so immediately when I see this, and then I see this, I know I have a buffer. All right, so sodium doesn't matter because it's always a spectator ion. It is always soluble, no matter what. So in this solution, the sodium is just floating around watching all this madness happen. Okay, and we've got 0.010 of the acetic acid and 0.010 of the acetate. Water is irrelevant, and H3O is at 0. So the products are going to increase, so it's going to be plus X on these on the product side, and we're going to subtract on the reactant side. All right, and then I'm going to plug these into the equilibrium expression. So it's going to be 0.010 plus X times X divided by 0.010 minus X. And that would be equal to the Ka. All right, so this X cancels out and that X cancels out. And then we'd multiply by 0.01 and divide by 0.01. So we'd end up getting that X is equal to 1.8 times 10 to the negative fifth. Well, that's the H3O, right? X is H3O. So to find the pH of the solution, I just take the negative log of this, right? Take the negative log of that, and I end up getting that my pH is 4.74. So I'm going to write that over here. All right, and then if I use the equation, right, I need to find my pKa. That's easy to do. You just take the negative log of the Ka, right? pKa is equal to negative log of the Ka. So if I plug 1.8 times to the negative fifth in there, I get that my pKa is 4.74. And then if I say, okay, the pH is going to be equal to the pKa, 4.74, plus the log of the base over the acid. Well, this one's the base, right? That's the base. And then this one is the acid. So it's going to be 0.010 divided by 0.010. So 0.01 divided by 0.01 is just going to be 1. And the log of 1 is 0. So this is 0. Like if you plug it in your calculator, you're going to get 0. So 0 plus 4.74 means that the pH is 4.74, and that's what we got here, right? We got 4.74. So you can either do all of this down here, or you can do this, but you can only use this for buffers. So you still have to be able to do rice tables and other stuff. All right, so for the next one, and I'm just going to erase some of my values in here. All right, so in the next one, I've got the same amount of acid, but I have much less conjugate base. So since I have less base, that means that my pH should be lower because I have more acid. So it's going to increase over here, and then it's going to decrease on the reactant side. So I'm going to plug in my values. Now this x becomes negligible as well as this x. So I'm going to multiply both sides by 0.01. All right, and then what I end up getting is, after those two cancel out, I'm going to get x times 0.005 is equal to 1.8 times 10 to the negative 7th. And then I'm going to divide both sides by 0.005. Okay, and I end up getting 3.6 times 10 to the negative 5th. And then if I take the negative log of that, my pH is equal to 4.44. So it is lower than the first one because we have less conjugate base, we have less base and the same amount of acid. If I use the Henderson-Hasselbalch equation, my pH is going to be equal to 4.74 plus the log of the base, which is the 0.005, divided by the acid, 0.010. All right, and if I take the log of 0.005 divided by 0.01, which is 1/2, or 0.5, you get negative 0.301. So if I add negative 0.301, I end up getting that my pH is 4.44. So it is the same value. And then on the last one, I'm not going to do the rice table. I am only going to do the Henderson-Hasselbalch equation. All right, so the pH will be equal to the pKa of 4.74, and the pKa is going to be different for every acid. And this time we have twice as much base as we did in the initial one, so the pH should be higher here. All right, so I'm going to take the log of 0.02 divided by 0.01, so log of 2, which is going to be 0.301, and add 4.74 to that, and I end up with 5.04. So this one is definitely higher than the first one because we have more base. All right, so I just wanted to show you that you can use both ways. This is pretty much it for this Henderson-Hasselbalch equation. Anytime you have a buffer, you plug it into the equation and get out your pH. All right, so you just have to recognize when you have them. That's the hardest part. So you need to be able to recognize when you have a conjugate acid or a conjugate base of a weak acid or a weak base.